The Burger King chicken sandwich is not going to be helpful.
All right, are we okay with this? So this part's going to be 1. Don't forget about that because when you're anti-differentiating, the 1 doesn't go away. This part we need to break into partial fractions. So let's just focus on that. X cubed minus 2x squared factors into x squared times x minus 2, right? So do you see what's going on here? What's the significance of x squared? Right, it's like x is a factor twice, right? So that's going to cause 2 partial fractions just for that, right? And then a third one for x minus 2. So x minus 2 is here. Your first denominator is actually what?
X squared.
The first one is x,
And then
to
X.
say that that was a factor, and then we have x squared to say that x was a factor twice. Does that make sense? Okay? And all of these numerators are going to be constants. So you're going to have a, b, and c. This is the one exception where you don't follow the rule that the degree of the numerator is 1 below the degree of the denominator, because technically this is degree 2 and this is degree 0. But when you are accounting for repeating factors, that doesn't change your setup of the numerator. The only time you have a different numerator setup is what we're going to do today, that we kind of, I think it came up yesterday in discussion, but we didn't have a problem that did it, where you have a quadratic that can't be broken down any further, right? So not like x squared, but something like x squared plus 1, which doesn't have any real roots. There's no way to break x squared plus 1 into 2 linear factors where you have real roots, okay? So in that case, you're going to switch from constant numerator to linear numerator. But in these, all these are constants. So now we solve for a, b, and c the way we've been doing. So clear all the fractions, multiply everything by the original denominator. So I'm going to have negative 4 on this side. What is a getting multiplied by now?
X and X minus 2.
Only one x, right? Because one of the x's is going to cancel. So there's only one x here, but there is also x minus 2. Does that make sense? Whereas the b, both of the x's cancel, and so you only have the x minus 2 here, right? And for the c, the x minus 2's cancel, so what's being multiplied by c? X squared. All right, does that make sense? Now we do what we normally have been doing to solve for a, b, and c. We can choose like convenient x values, right? What would be a helpful x to use here? 0 would be good. If I choose 0, I get negative 4 equals, now which thing is still going to be there if I'm letting x be 0?
B.
B, and b's coefficient would be negative 2. So negative 4 equals negative 2b, that means b is 2. Okay? What else is helpful to use for x?
2.
2, okay? If I use 2, which one am I going to solve for? C, so negative 4 on the left equals 4c, so c is negative 1. And now I'm kind of out of helpful x values, right? There isn't any other x. The thing I still need to solve for is a, but there's no value of x that I can use that will just leave me with a. On the other hand, at this point, I already know what b and c are, so really I can use any x value, plug in for x, plug in 2 for b, plug in negative 1 for c, and you're going to be left with only a in your equation, right? So what do you want to use for the third x?
1.
1, okay, we use 0 and 2, so 1 seems good. So if I use 1, still a negative 4 on the left, and then check my math here. 1 is for x, so this is 1 times negative 1, that's negative a. And then I would have negative b, but b is 2, so that's a minus 2. And I would have 1 times c, but c is negative 1, so that's a minus 1. Does that make sense? That's negative 3 combined over here. So if I add that over here as positive 3, I'm going to end up with negative 1 equals negative a, which tells me a is 1. Is that okay? All right. So now, let's see if I can fit a little bit more work in here. We can go back to our original problem. Remember, the original problem had this thing first, which is 1. So I'm actually integrating 1 And then this thing got separated into these three fractions. So now we know what those are. A was 1, so it's 1 over x. B was 2, so it's 2 over x squared. And C was -1, so it's minus 1 over x minus 2. Is that okay? All right, and then I'm going to anti-differentiate all of that. I guess I can probably do that here, and then I'll have to move over. So let's do these term by term. 1 does not go away, right? What's the antiderivative there? X plus 1 over x is easy. ln x. Okay, what about 2 over x squared? That is not an ln, right? Don't write 2 ln of x squared. It's like 2x to the -2. So the antiderivative would be -2 x to the -1, which is like -2 over x. So it'd be -2 over x, right? Power goes up by 1. Okay, and then the last one is minus ln x minus 2. Okay, no plus c's here because it's definite. We have to plug in 4 and 3 and then subtract. And we have to get the answer in the way they asked for it. So let's do that part over here. I'm plugging in 4 first. So it's 4 plus ln of 4, I think. Minus 2 over 4, so that's minus a half. Minus ln of 2. You good there? That's what you get when you plug in 4. Minus what you get when you plug in 3, which will be 3 plus ln 3 minus, is it 2/3? And then minus ln 1. Okay? All right, what can we do with ln 1 right off the bat?
Take it out.
That's 0. Okay? Now we're going to have to combine, basically you're going to combine all the non-ln terms and then all the ln terms, right? So the non-ln terms, we have 4 minus 3, so that would be 1, minus a half, so that would be a half, and then this is actually plus, because of this negative, plus 2/3. So we have a half plus 2/3, but we need that combined into one fraction. What is that? How much? Not 5/6. This is 3/6 and this is 4/6. 7/6, yeah. 7/6, okay? And then the ln terms, we have ln 4 minus ln 2 minus ln 3. So can we put that together in one ln expression? ln 4 minus ln 2 plus ln 3 would be ln 2. ln 2 minus ln 3 is ln 2/3. Okay? I didn't mention this, I forgot about this language. So it says, we have it in this form, right? A fraction plus ln of a fraction. A, B, C, and D have to be positive integers, they all are. What is this business about neither A and B nor C and D share any common factors greater than 1?
It's simplified.
That's a long way of saying, like, make your fractions reduced. We have 7/6 and 2/3, they are. Okay? Everybody okay there? Any questions? Yeah.
That means so A sure. What do you mean?
It seems like you want to have some more discussion about this. I can be included or excluded. It's up to you. But I feel that we don't want to move on quite yet. Is there something you want to add?
Yeah.
What are you, I said.
Let me write this out. Okay.
Minus 3 is half.
I used to be so good at answering.
What is so hard to compute about
Why is on catches?
I don't know.
All right, are we good? That's not
Oh, yeah, so you have to multiply it by negative 6. Because when we, like,
I just forgot to do like basic rows.
negative.
Oh, that's because someone else. Okay. All right, are we okay?
This has to be, so we can multiply by negative 1, or can we divide it?
All right, so let's go through a couple more examples that involve stuff we didn't get a chance to talk about yesterday, okay? So the first one is we have irreducible quadratic factors, okay? This is like the worst possible case you can come across when you're looking at a denominator that factors. What might happen is your denominator factors into quadratic factors that can't be broken down. There's actually no such thing as higher than quadratic that can't be broken down. It's always possible to break down cubic or quartic or whatever. Now, it doesn't mean it's easy to do. This problem, if it was on paper 1, might well be presented to you like this, where it's already factored for you. Because they are not going to test you on all that pre-cal stuff with like rational root theorem and Descartes' rule of signs, where you have to like spend a long time trying to figure out what the factors are, okay? This would have been a quartic initially, right? And since it's quartic on the bottom and cubic on the top, it is proper, so we don't have to worry about dividing. But it turns out that the quartic just factors into 2 quadratics that both don't have any real roots behind.
Would breaking them up into complex roots not lead you to
Like if you did x minus and plus I, yeah. We don't ever like bring the complex numbers in. I'm not sure that I think you have to, like then you're sort of talking about a more extended version of calculus than what we have here. It's called complex analysis, where you do like calculus on functions that have that can have complex variables in them. You would never do that in what we're doing. I don't actually know if you tried to just set it up with that. I don't know if you would just after a while return to the answer we're going to get anyway or not. But I know that you wouldn't see. They would not be asking you to break it down into complex factors. There's some other weird stuff that happens in calculus once you open it up to like a complex domain instead of a real domain.
So without the calculus, like even if you were doing partial fractions, like removed from the integration side,
Yeah.
it wouldn't lead you to the same. Like,
I'm not sure. I haven't tried it, so I don't know for sure if it would or not.
okay.
I don't know. All right, so let me show you what the setup is here. Since we only have quadratics and they can't be broken down any further, we're only going to get 2 partial fractions here. One for each denominator factor. So we're going to have x squared plus 1 and x squared plus 2 as the denominators. And this is the case where if the quadratic can't be broken down any further, then we're following the process that the numerator degree is 1 below the denominator degree. So if this is only degree 2, the numerator has to be degree 1. So instead of the general constant, like ABC, whatever, I need a general linear function, which is represented as ax plus b. So this would be ax plus b. And then I need a second one over here, so this is going to be cx plus d. Okay? All right, now we proceed the way we have before, clear all the fractions. So I'm multiplying through by the original denominator. So I just have x cubed plus x squared plus 2x plus 1. And then over here, this ax plus b will get multiplied by what? X squared plus 2, the other one, right? Because the x squared plus 1 will cancel. And the cx plus d, the x squared plus 2 cancels. And this gets multiplied by x squared plus 1. Now, in this scenario, the shortcut we've been using doesn't really help much because there are not any real x's we can choose that will eliminate all but one of the variables, right? Because none of these have any real solutions. So here's a case where I would not use the shortcut method, but we've used the shortcut method so often, like in BC Calc, since they said they were never going to give you this kind of thing, we never really had a reason not to use the shortcut method. But do you remember what the alternative is? Like what the shortcut method is a shortcut for? Like what's our other way of finding A, B, C, and D if we're not just going to choose x values here?
Like a system.
Anybody remember what you can
Like a
do?
system.
Well, you could, we could just arbitrarily choose, since there's no x values that are going to kill all of the things except one, if we pick an x, we're going to probably get all 4 things in there, and then we could, at worst, we could have 4 equations with 4 unknowns. Sometimes you need to do that. But in this case, we don't have to be, it's not gonna work out that bad if we do it a different way than just like plugging in values. That's what I'm thinking, like what's another way to set up a system other than plugging in the values, Joey? Yeah, by the powers of x, right? So if I FOIL this out, I'm gonna get ax cubed plus bx squared plus 2ax plus 2b, right? And the other one's gonna be cx cubed plus dx squared plus just cx plus d, right? So if I match that up to x cubed plus x squared plus 2x plus 1, do you see we can go power by power of x? There's like x cubed terms, x squared terms, x terms, and constant terms, and we can just equate the coefficients for each power of x. Like if we take x cubed, the only x cubed on the left side is this one, and it has a coefficient of 1. So the total of the coefficients of x cubed on the right side has to add up to 1. Where are the x cubed terms on the right side? What are their coefficients? A plus c. So a plus c has to be 1. Okay? Now, sometimes when you do this, maybe there's only one x cubed term over here, and then you would know what that value is right away. In this case, we're not quite that lucky. We have 2 variables with 1 equation, so I can't use that to solve for a or c right now, but at least I only have 2 variables, not all 4, right? So I'm going to do this with the other terms, the other powers of x, and then we'll see what we have in terms of the system. But the worst case here is that you have 4 equations, 4 unknowns, right? In this case, we're going to be in a situation that's better than that, okay? When I go to x squared, the only x squared term also has a coefficient of 1. And what are the x squared terms on the right side? B plus D. So that's another equation that only uses 2 variables. It doesn't overlap with the 2 we already had, so like those 2 together aren't helpful. But you see what happens when I look at the x terms? I have a 2 over here, and which terms have just x in them on the right? 2a plus c. So now, if you match the first and third equations, you have a 2 by 2 system. Like we could use just those 2 and get both a and c. And you notice if we do the last one, what's the thing we haven't done yet? Well, we did x cubed, x squared, and x, so the only thing we have left is the constants, right? The constant on the left is 1. The constant terms on the right are 2b and d. So 2b plus d is 1. And that means we can match these 2 together and find b and d. Make sense? If this turned out to have all of these equations involved all of the variables, so you had a 4 by 4 system, you would not have to solve that without a calculator. That would be like a paper 2 question. And how would having the calculator help you solve the system? Like what's something we have done this year that would let you solve a 4 by 4 system with the calculator? Matrices. That's what I would do. Okay. See, that's another reason why I want to keep the matrix unit in case you have something like that. You're not thrown off and saying, oh my gosh, I have to solve a 4 by 4 system by hand, right? Because IB would not make you solve it by hand. So let's take the A and C equations first. I have 1 equals A plus C, and I have 2 equals 2A plus C. Okay, and you see this is set up if I subtract, the C's will go away. I'm going to subtract up because I'm partial to positive results, right? So if I go this way, these are gone. 2A minus A is A, and this would be 1, so A is 1. And if you know A is 1 and you use the top equation, what does C have to be?
0.
0. So right away we have the first 2. Right? Then I can do the same thing with the B and D equations. So we have 1 equals B plus D, and we have 1 equals 2B plus D. I'm going to subtract up again. The D's are gone. 2B minus B leaves me with B. 1 minus 1 this time is 0. So B is 0, which implies D is 1. All right, now I have them all. Right? So now I can rewrite the original integral. It was ax plus b. A is 1, b is 0. So this linear function is actually just x. Is that fine? And the denominator is x squared plus 1. And then the second one, cx plus d, c turned out to be 0, but d was 1. So that's just the constant 1. over x squared plus 2. Okay? So now we have to integrate those two fractions. Let me come over here for that. Okay, the first one should not be a problem. Can you figure out how we're going to do x over x squared plus 1? How would I do just this? Yusa, u would be, okay? That makes du 2x dx. I have x dx, but not the 2. So 1/2 du is x dx. That means this is going to have a 1/2 out front. And then what is this in u form? One over u du. So that's easy. Antiderivative will be 1/2 ln u. I'll wait for the plus c because we have the other part to do also. But I want to put this back into x terms. So it's 1/2 ln
X squared.
x squared plus 1. And you see I don't need absolute value here? Why is that again? It's not negative, right? Okay. Okay, so that's that one. Now the other one, I want to show you something about this one. X squared plus 2. Okay, if this was a 1 instead of a 2, it would be easy. Do you know what it would be? Don't you recognize 1 over x squared plus 1 as the derivative of a function? Inverse tan, right? So this, if this was a 1, and it's not, unfortunately, but if it was, this would just be inverse tangent of x, okay? It's still going to relate to inverse tangent, and I'm going to show you how to figure this out. Don't write down what I'm about to do, okay? Because you won't have to do what I'm doing. I'm going to show you, IB has helped you out with problems like this, and I'm going to show you how they helped you out, but if I just show it to you, it's going to seem like it came out of complete thin air. So I want to show you how we're getting this, but then you won't have to do what I'm writing on the board. So write this down only for your own enjoyment, not because you're going to have to study this later, okay? We said we would like this to be a 1, so I'm going to factor out the 2 and make this x squared over 2 plus 1. Does that make sense? And since this is factored out, this can now come all the way out in front. So this is 1/2 integral 1 over x squared over 2 plus 1. And then I'm going to do a u substitution here. I'm actually going to say if this was u squared plus 1, this would just turn out to be inverse tan of u. So I'm going to say I want to replace the x squared over 2 with u squared. I'm kind of reverse engineering the substitution here. That would tell me that u should be what? X over root 2, which makes du 1 over root 2 dx. We don't have the 1 over root 2, so I'll move the constant over here. So it's going to be root 2 du equals dx. Okay, and now if I write this over here, I already had the 1/2 out in front. I'm bringing out an extra root 2 as a constant. So this becomes 1 over, and we said this would just be u squared plus 1. So that's root 2 over 2 is the same as 1 over root 2, right? And then this would just be inverse tan of u. And then we just replace the u. It's inverse tan of x over root 2. Okay? So this is the answer that we're looking for. But I said don't write all that down because you won't have to do that. I'm going to direct you, if you have it handy, to the formula packet. Okay, at the very end of the formula packet, not the very back page, but right before that. So the second to last page, at the bottom, it's the second box up from the bottom. It says standard integrals. I don't know why IB calls these standard integrals, but there's 3 in the box. The first one, I don't think you even need to be in the formula packet. It says the integral of a to the x is a to the x over ln a. That's just like a basic rule you learned in BC. I don't know why they just decided to put that one on the formula packet. But the next 2 are very useful because they save you the work I just wrote on the board here. The middle one is the one we're about to use. It's the one that uses inverse tan. And the last one is a similar one that uses inverse sine. So in the packet, if you don't have it right now, this is what's in the packet. It says integral of 1 over a squared plus x squared is 1 over a inverse tan x over a plus c. Do you see that this is exactly what we have here? What would your a be? If we see 2 here, that's a squared, right? So what's a? Root 2. So by the packet, that integral, when you see a 2 here, is 1 over root 2 inverse tan x over root 2. That's what we got right here. So they are telling you they don't need to see this. If you get this integral, you can just go to the packet and say that integral has this result, and you're done. Okay? And there's another one that's similar for inverse sine. Those are really helpful. They're saving you having to do some annoying substitutions. I'm going to talk to you more. We're going to do integration stuff all this week, and I'm going to talk to you more later in the week about some other things IB does that are nice to you in terms of substitution stuff. This is partly because the IB test is not a test just on calculus, so it's not like people have been studying only calculus and are taking the test at the end, like what AP was, right? AP doesn't give you these nice, helpful hints. They would have you figure that out. But IB has some in the packet, and there's some other helpful things they'll do even when stuff's not in the packet. I'll talk about later. Okay? All right, so we're basically done with this one, right? The answer to this part was 1/2 ln x squared plus 1. And then this one by the packet says 1 over root 2 inverse tan x over root 2. And then plus c. And we're all done. Okay? Make sense? All right. Let's try another one. Raise the level of fun. This was kind of fun. We need more fun. This one is more fun. Okay. You see what I did with this one? I factored this for you. That was nice of me. Okay. When it factors into a quadratic that doesn't break down, x squared plus 1. And then you see what's going on here? What is this? X minus 1 squared means you have to account for repeated, right? So I combined two kinds of fun to make even better fun, right? Repeated factors and quadratics that don't break down. It's all the special cases that AP said we're not worrying about. IB says, no, we love these problems. We don't worry about them. We just like to do them. Now, I could have made it even more fun. I could have had triple fun, but I didn't want to cause any harm anywhere. Do you see, what's the degree of the bottom?
4.
It's actually 4th degree, and it's only 3rd degree on the top, which means no dividing, right? I could have made that like an x to the 5th or something, but let's not get crazy. Okay. So let's break this up. X cubed plus 2x minus 1 over x minus 1 squared times x squared plus 1. How many partial fractions will I have? We've got repeated factors and a quadratic that doesn't break down. So how many denominators am I going to have? 3, right? The first one should be x minus 1. But because x minus 1 repeats, the second one is x minus 1 squared. And then you have the quadratic that doesn't break down, x squared plus 1. Okay? The first two, the numerators should be similar. We just have constants there. So you've got a and b. But this is the case where you have a general linear term, so this would need to be like cx plus d. You okay there? Now clear the fractions. X cubed plus 2x minus 1. What is a multiplied by here? 1x minus 1, because the other one cancels, and x squared plus 1. Right? B is going to only be multiplied by x squared plus 1. And the cx plus d numerator gets multiplied by x minus 1 squared. All right. This one is going to be kind of a hybrid in terms of solving for the A, B, C, and D. There is one especially convenient x value to choose that will let me solve for one of those 4 things right now. Do you spot that? What x could I use?
1.
1. If I use 1, everything over there will be gone except which constant? B. Okay? So if I plug in 1 here, I get, those are going to cancel. It's just going to be 2. And everything here is gone except this term, it's 2b, so b is 1. Okay? Now, to get the other ones, we could do what we just did before and expand everything. I'm not loving that idea that much. There's like a lot of expanding to do. Or we could choose 3 more x values. And if we choose 3 more x values, remember we already know b, but we may get a, c, and d as variables, and we might have a 3x3 system to solve. This would definitely be a with calculator problem, so we don't have to worry about a 3x3 system. Like if we get that, we just use matrices to solve it, okay? And that's what we would get whether we expand it or not. Like either way, we're gonna get a system unless we find that like some of the equations don't use all the variables, okay? The only thing I did before I just went ahead and plugged in x's was I did notice that there aren't, I have x cubed over here first, there aren't that many ways you're gonna get x cubed over here. Do you see the only possible x cubed terms would be right here, you have one with a coefficient of a. This doesn't have any. And the only way you would get it here is after you expanded this, there'll be an x squared multiplied by this cx would give you an x cubed, right? So x cubed over here is 1. And over here, you're only gonna have a and c. So I'm gonna put that this is coming from x cubed. Okay, now by itself that doesn't help me because I have both a and c in there. I can't solve for either a or c. But that's an equation with a, c, and d in it, just that d doesn't appear. I need 2 more equations to be able to make the 3x3 system. So at this point, I would just choose 2 other values of x. And try to choose values that are like not troublesome to evaluate. Like what would probably be your first choice?
0.
I would choose 0. 0 will actually get rid of the c right there. Right? So if I choose 0, this side is -1. And then over here, I would get negative a plus b, but we already know b is 1. And then over here, I just have d times 1. So plus d. So that's my second equation. I need 1 more. I've chosen 1 and 0. What do you want to choose for the last one? Did I choose 2? I don't have my sheet. I think I did. I think I picked 2. I could see 2 or -1. Okay. All right, if we pick 2, 8 and 4 is 12 minus 1 is 11. Okay, over here, this is 5 times 1a, so 5a. This is 5 times b, but remember b is 1, so that's just a 5. And then I'm picking 2 here, so this is 1 times cx plus d, but x is 2, so that's plus 2c plus d. That make sense? All right, so I'm going to write my system out. I've got a plus c, and no d in that one, equals 1. Then I've got negative a, no c in this one, plus d, and this would be equal to -2. And then this one has all of them, 5a plus 2c plus d. And that is going to be 6 because I got to move this 5 over. So there's my system. And remember, we also already knew, whoops, that b was 1. Okay? So at this point, I would go to the calculator and make a matrix. And how are we going to use the calculator to solve the system represented by the matrix? Like once we put the matrix in, then what do we do? RREF. Okay? Does somebody have this written down? These 3 equations? Because I'm going to switch to the calculator, but I don't want to have to keep switching back. Somebody have those? Okay. All right, so all right, I'm going to enter, it's a 3x4 matrix. Does that make sense? First row, so we're going to have A, C, D, right? We don't need B because we already know B. So A, C, D, and then the numbers. So what's the first equation?
A plus c equals
So 1, 1, no D, and
1.
then what's the
1.
1? Okay. Next one?
Negative a,
-1.
and then 0,
Okay.
and then 1, and then -2.
-2. And then the last one, 5, I remember?
Yeah, 2.
2.
1.
And 6, okay. All right, everybody okay there? Then I'm gonna go to RREF. That's under math. Matrix A. And I'll make this into fractions. Okay, what is that telling us? How do we interpret that result? What's A?
3 halves.
3 halves, C, negative half, D, also negative half, okay? So C, A's 3 halves, the other two are negative half each. So we've got 3 halves, negative a half, negative a half. Okay? All right, let's write down what the integral is. I don't know that we'll have time to solve it all the way, but I think you'll be able to see what you need to do for this one. Okay, so it's a over x minus 1. A was 3 halves. B was 1, so 1 over x minus 1 squared. And then negative a half x minus a half, right? C and D were both negative a half, and that's over x squared plus 1. Is that fine? So this one's easy, right? This is just 3 halves ln of x minus 1. This one doesn't use ln. This is like x minus 1 to the negative 2. So the antiderivative would be x minus 1 to the negative 1 over negative 1. That's minus 1 over x minus 1. And then this one, what I would do, since these are both negative a half, take that out, and now you have this. And that actually looks tricky, but the secret to this one, and we'll go over this more in the coming days, if you break apart this fraction into 2 separate fractions, remember you can split up the numerator, you get x over x squared plus 1 plus 1 over x squared plus 1. And we've done both of these today, right? This one was u substitution, and it comes out to like 1/2 ln at the bottom. And what is this one? Inverse inverse tangent of x. That's all it is. Don't forget there's a negative 1/2 in front of both of these already, right? So that'll take care of that one. Okay? All right. So the homework on the back, 7, 8, 9, 10, incorporates the stuff we just did here. You're going to see some repeated factors. You're going to see some quadratics that don't break down. Depending on how big your equations are to solve for A, B, C, and D, you might need to use the calculator. You can. Okay, that's fine. All right, and then we're going to go on to more integration the rest of this week. But